Hi, Chem students. Let's talk about drawing simple Lewis structures for covalent compounds. So covalent compounds are a little bit different. Remember that instead of the electrons being transferred from one species to another, one atom to another, to create two different ions which are held together by a Coulombic force, the electric force, in this case, the electrons are going to be shared between the two atoms so that they can fill up or try to fill up their outer shell as best they can. So for different atoms, filling up their outer shell is different. So you need to always keep track of which atom you're talking about. Some points to begin with. First off, what we're going to be doing is we're going to be representing every electron that we can. We want to keep track of them all. So we're first going to know that any electron that's not part of a bond, not part of the covalent bond, is going to be expressed as a dot. Then anything that is a bond will be represented as a line, and that line will represent two electrons. So it's possible that more than two electrons will be part of a bonding situation, and therefore we may have multiple lines or multiple bonds in any particular molecule. We're going to show all these electrons, not just the bonding and not just for the central atom. So typically there's going to be an atom at the center of all this, and other atoms will be connected to it. And we're going to put electrons on everybody at all times, and we're going to use lines only representing the bonds, and that's how we're going to do things. So that way we're all on the same page from the start. Well, no better way to do this than to begin with an example. Let's look at hydrogen fluoride, HF. So if I have a hydrogen, it's going to look like this. It's going to have a single electron, and it's 1s1 electron configuration. And if we look at something like fluorine, fluorine has 7 electrons around it. So fluorine is currently at if you think about it, it's a 1s2, 2s2, 2p5 electron configuration, while hydrogen's at a 1s1. So what would be great is if hydrogen could fill up its outer shell and have a 1s2, and if fluorine could fill up its outer shell and have a 1s2, 2s2, 2p6, then they would both look like a noble gas. Hydrogen would look like helium, and fluorine would look like neon. So that being said, what can happen here is we can imagine these guys kind of getting together, and instead of transferring electrons, we could make, and just for fun, I'm going to make the hydrogen electron, instead of calling it a dot, I'm going to make a little X there. That's still an electron. And then I could put the fluorine like this. And what I've done is I've allowed the electrons, I've allowed two of the electrons to be shared between the two. So right here, these two electrons are being shared, and that's the covalent bond that's formed between hydrogen and fluorine to make HF, hydrogen fluoride. So if you were to cover up the fluorine, and what I'm going to do is I'm going to kind of draw around it right now. If I was to cover up this part right here so you couldn't see that, the hydrogen would look like it has two electrons, the two electrons in the yellow that's been highlighted, correct? All right, we could also look at it from the other direction, and we could say, what if we were to cover up the hydrogen? If we did that, then the fluorine looks like it has 8 electrons around it. So they both look like they have a full outer shell, and that way they're both, for lack of a better word, happy. That just really makes them stable. So this right here would be what we would call a single bond, because there's 2 electrons being used, and we would end up drawing this structure as such. We would draw it as HF, and then of course we'd finish it off with the other electrons, the non-bonding electrons that are now around it. So this is the proper Lewis structure for HF. All right, fantastic. Let's try a couple more examples, a little bit more complex, but they're still simple. So methane is CH4, and just for now, I'm going to tell you that hydrogen can never be a central atom. Therefore, you know the central atom in this particular guy is the carbon. So if we draw a carbon, it's going to have 4 electrons around it. 1, 2, 3, 4. And every hydrogen is going to look like this, with 1 electron around it. So the only way to make this all fit together is if each electron made a bond with one of the 4 hydrogens. So this right here says there's 4 hydrogens. I've got 1, 2, 3, 4 hydrogens there. I'm just counting that. I don't want to write that down on my structure or anything. So now I've got this Lewis structure currently set up. All the electrons are accounted for, and if I look at it, the hydrogens all look like they have 2 electrons near them. And the carbon, if you really take a good long look, if I highlight and we ignore the highlighted region, the carbon sees 8 electrons around it. Just to help you out, it sees this. And that's 8 electrons. So the carbon feels like it's now a 1s2, 2s2, 2p6. It's got a full outer shell. So everything feels like it's got a full outer shell, and this is a very stable molecule. So methane, natural gas, has a Lewis structure that is this. So that represents all the electrons that are in this atom. You can always double check by counting. Each hydrogen brought 1 electron with it, so that's 4 total. The carbon has 4 in its valence shell, so that should be 8 total. Each bond that you see here, each bond has 2 electrons. 4 bonds times 2 electrons each is 8 electrons. So we can double check our math and make sure we've used up all the proper number of electrons. Let's do the same thing now for ammonia. So nitrogen has 5 electrons around it, and each of these hydrogens has 1, so that's 3 times 1. So once again, we should end up with 8 electrons total around us when we're finished. So we just look at the nitrogen. It's going to be 1, 2, 3, 4, and then the 5th one's going to go right there. All right, so there's a hydrogen. Here's what it's going to look like. If we put that together, you can imagine now that each one of the hydrogens is going to be able to go into these spots right here and make a single bond with each of those unpaired nitrogen electrons. So we would draw the Lewis structure as such. All right, so when we get finished with something like this and we feel like we've got it correct, we need to turn those bonding electrons, which I'll highlight once again, these bonding electron pairs, they turn into lines so that we can draw our Lewis structure as such. Nitrogen, hydrogen, hydrogen, another hydrogen, and then don't forget the lone pair of electrons there. Great, let's do one more example. Let's do water. So if we look at water, water has the oxygen with 6 electrons around it. It has, each hydrogen has 2 times 1. That's a total of 8 electrons one more time. So we're seeing this number 8 come up a lot. That's called the octet rule. And most central atoms will try to make an octet, or possibly even more. There's a few exceptions, of course. Boron and aluminum, they often make molecules with only 6 electrons around them. And then if you go into the N equals 3 or N equals 4 nonmetals, they can start to go beyond the octet. This is for a later, we'll have this in a later story, but they can go beyond 8 and go to 10 or 12 around them. So we'll see how to handle that in just a moment. Anyways, so for this, we're going to have oxygen with 1, 2, 3, 4, 5, 6 electrons around it, and each hydrogen will have its 1 electron, and you can imagine then that each one of the hydrogens can come right into this spot and make that non-bonding or that unpaired electron become a pair and make it a bond. So we get something that looks like this. And that is water. Good old H2O. All right, so what do we notice from this? Well, it turns out that if we do a whole bunch of molecules that have oxygen as a central atom, or a nitrogen as a central atom, or as a carbon as a central atom, we notice something, that carbon tends to make 4 bonds. and that nitrogen tends to make 3 bonds and have a lone pair. And then oxygen likes to make 2 bonds and have 2 lone pairs. All right, so this, if we know this, we can easily create a lot of these Lewis dot diagrams without a lot of hassle. Okay, so for example, how do we handle something like carbon dioxide? Well, if I look at carbon dioxide, carbon likes to make 4 bonds. And it's only got 2 things that it can bond to. So there's only 2 ways it could possibly bond. One is to make 3 bonds over here called a triple bond and 1 over there and have an oxygen somehow involved in both of these. We'll have to figure out how those electrons work. But the other option is to have 2 bonds on either side. Now, I'm hoping that you, as you look at this, you think, boy, it kind of makes sense to have some kind of symmetry or consistency in a molecule. And it turns out that this one on the right, which is more symmetric, this is the correct structure. Let's see how that's kind of, how we can logic through this. But did you see how quickly I got to it just by knowing carbon must make 4 bonds? So here's how you can go about thinking of this molecule and doing the whole thing with the Lewis dot structures. So here we go. Carbon has 1, 2, 3, 4 electrons. Here's an oxygen with 1, 2, 3, 4, 5, 6. So let's ask a question. Let's ask, how many electrons does the oxygen need? How many electrons does the oxygen need to get an octet? So to get to 8 electrons, how many does it need? And the answer is it needs 2. Where's it going to get those? Well, the central atom is carbon, so it's got to get those electrons from the carbon. So let's put a carbon right here, and let's put 2 of its electrons right there. Fantastic. And now let's put our oxygen around it. Great. And now I'm going to make the oxygen have little X's for its electrons. Make that a little bit closer in size. All right. So there we go. The oxygen has 8 around it, and the carbon now has 2 around it. The other oxygen also needs to bond to the carbon. The carbon has 4 total electrons, so it can put those other 2 right here, and it can do the same thing and say, aha. There we go. So the oxygens are all happy. They've got 8 electrons around them, and it seems like we're done. But there's a problem. Carbon doesn't have 8 electrons around it. Carbon only has 4. Its original 4. So in other words, it gave all the electrons in the sharing, and none came from the oxygen. So instead, we can't use this one. We have to have a different setup. So what we would have to do is we have to think, okay, here's our carbon donating 2 electrons to one of the oxygens and 2 of the electrons to the other oxygen. So we've set it up so we know how the carbon must behave to get the oxygens to 8. But now let's ask the question, how many electrons does the carbon need to reach that full octet? And the answer is the carbon needs 4 more electrons, and it's going to try to get 2 from each of these oxygens. So the oxygen would give 2. And now we have a situation where the carbon sees 8 electrons around it. Let me highlight those 8 electrons. There's the 8 electrons that the carbon sees. It feels like it's got part of all 8 of those, and therefore it's mimicking being a noble gas, being a neon. All right, so the final structure then for carbon dioxide is C, double bond O, double bond O. And believe it or not, that fits our trend of each carbon having, of carbons having 4 bonds about them. And also, notice that the oxygen has 2 bonds. Each oxygen has 2 bonds, which is also part of our trend. So carbon dioxide is an excellent example to show us how we need to keep track of the number of bonds that are the tendency for these atoms to make, and how the electrons get spread out about them, and where the lone pairs end up going. And by lone pairs, I mean these right there. Those electrons are alone, they're pairs, but they are not part of a bond. So we would not write them as a line. We keep them as single dots so people know that they're available for bonding. And So essentially, that's how chemists will start to imagine the reactivity of molecules by looking at where the electrons are in bonds and where they are not in bonds, and start moving them around in their mind to see how they might make new bonds and break old bonds. That's another story for another class, but it's a start. So here's our beginnings to doing covalent molecules. We've now seen that there are things called single bonds, double bonds. This carbon dioxide has 2 double bonds, and there's also triple bonds out there. We'll talk more about that in another session.